Recording is rolling. It's Friday, August 26th, and here's what we got lined up today. So, oh yeah, I do want to remind you guys. You guys probably know about this. It's going to be a special rocket launch Monday morning. So by the time next time I see you guys, so when you guys are coming to school Monday morning, 8:30 in the morning, 8:33, look to the north, and you should see a rocket launch to the moon. Now there's no astronaut there. Oh yeah, go ahead.
Is it excused if you do not watch?
I didn't see anything like that. Unless I missed an email or something, but not that I know. Yeah, so um yeah, no, there's no astronauts on this one. The last manned mission, I think it was 1972, so back in the 1970s. The last time we sent anything to the moon, I just looked up, was like 2014, so like 8 years ago. So yeah, it will be a cool launch, and it needs an extra blast to escape Earth's gravity compared to just like satellites that just need orbit. So there you go. Uh, last couple of days, we've been working on a lab to set up kinematic motion that we use to derive these kinematic equations, which we reviewed, guys. Most of you guys turned that in already. In fact, if you did turn in yesterday, it should be back in your folder. You guys see those folders that you from the lab table? So they're roughly alphabetical. A is here, then it winds around, and Z is over there. So any papers I pass back, that's by last name, right? So prior stuff. If you haven't turned in your lab yet, get that in that gray tray right there, and then I will grade that and give you guys some points. Okay, so I think a pretty good way to round out this week is to recap some linear motion equations maybe from a different point of view. So there's this guy named Paul Hewitt, also taught physics, conceptual physics. Actually, I'm drawing from a lot of his materials for this class. For example, there's a page I gave you guys. I know we haven't got to this stuff yet, but I gave you guys a paper anyway. Has some equations on one side, has some conceptual questions on the other. These conceptual questions I pulled from this guy's materials. So I'm going to play some videos from him where he also explains the kinematic motion that we've been working on this week. So you guys get to see a different perspective. If you like his style in his videos, then I've uploaded all his videos. I put them all in a zip folder on Google Classroom. So if you wanted to look ahead a few weeks, a few months of this class, then all the stuff is there. So let's look at what we built up to yesterday, and then I'll flip over and you guys get the new perspective. So you guys were rolling Hot Wheels cars down inclines, and we use that to ultimately put these equations together, these kinematic equations that govern the motion of those cars. Then I also set up for you guys a different story yesterday. You go to edge of cliff, drop a ball, okay, which is like a sped up version of your guys' lab, and it's the exact same equations. Okay? And there's only 5 variables that we're juggling around here, and it looks like a lot, but there's really only 5 variables. There's how much time has passed in seconds, right? That maybe the car was rolling down. There's how far the car rolled, right? X, displacement. I see 2 velocities. You guys see initial velocity and final velocity? So while your car was rolling down the incline, was it speeding up, going faster, faster, faster? So between the beginning and the end, it had a bajillion different velocities. But for these equations, you only care about 2. You care about the starting one and the ending one. Right? How fast at the beginning, how fast at the end. Right? In fact, if you guys released your car from rest, what was your initial velocity? Just 0 if it starts from rest, right? Which simplifies these equations a little bit. Okay? And there's one last variable on here. So we got time, displacement, initial velocity, final velocity. The last one is this one, A, acceleration. Now, it was a little more involved. That's the rate change of velocity. That's how fast you're picking up speed. So a good example is like if you're in a car, you step on the gas pedal, so you see that speedometer needle moving. The rate that the speedometer the rate that the needle moves, that is your acceleration. If you slam on the brake, you're slowing down. That's also kind of acceleration. It's a negative acceleration, but you can calculate it. Okay? So you go. Those are the only 5 variables. Here's how they're all connected. There you go. So I think now is probably a good time. Let me switch over, and you'll get the Paul Hewitt recap of all this fun stuff. Here we go.
First definition for motion is how fast you move. That's speed. So speed, we define speed to be speed's measured in like miles per hour. So it's distance compared to time. So speed is simply distance compared to time. If I travel 60 miles and I do it in a time of 1 hour, what's my overall speed? Try it. 60 miles an hour, okay? Let's suppose I go 70 miles in 1 hour. What's my speed? 70 miles per hour. Let's suppose I go 100 miles and it takes me 2 hours. What's my speed? 100 miles per 2 hours or 50 miles per hour, right? Can you do metric units? Let's suppose I go 60 kilometers and it takes me 1 hour. What's my speed? What is it, gang? 60 kilometers per hour. To say that you know your velocity is to say you know something else besides how fast you go. Do you know what it is? Which direction you go. Like an airplane pilot says, my velocity is so many kilometers per hour north. Speed plus direction. So to say something's moving with a constant velocity is to say something's moving with the speedometer reading staying the same, but also the compass reading staying the same. So velocity is speed, but with direction implied or specified. So the symbol for speed will be the symbol for velocity, and that's V, the velocity. So I can put this in shorthand notation and come up with our first little equation. And that's V equals D for distance divided by time.
Now, in this class, I've been using X for displacement instead of D, but it's the same idea. There's a lot of characters used for some kind of displacement. You use X, you could use D in this case. H, possibly if there's a height change, right? Like remember the cliff yesterday, a height change. Sometimes Y is used. So he's saying velocity is speed, but also direction. Hey, do you guys think if you're moving forward, that might be like a positive value for velocity? And if you're in reverse, like backwards, that might be like a negative value for velocity. So when you're applying those equations, you might have positive or negative values, right? Or how about this? Edge of a cliff. You drop a ball down, or what if instead you throw a ball upward? So when the direction of the ball upward and gravity pull downward, the opposite directions. So I bet if you set up an equation, there's going to be a negative sign somewhere. Okay. And also speaking of direction, you guys remember how acceleration is something that you can feel, right? So speeding up forward, you feel like you're pushed back into the seat in the car seat. If somebody slams on the brake, you feel like you're thrown forward. So it's like a change in motion, right? But do you guys remember the third control that you can also feel something, which is like the steering wheel? Now, can you have constant speed, but also be changing your direction? Can the speedometer needle point at like 30 miles an hour constant, but also you're going around a curve? Yeah, and you can also feel that. Now, that idea we're going to save for a few weeks from now. Right now, like for the next couple weeks, all we're interested in is just forwards and backwards.
Ordinarily, your ratio of distance to time may change. And sometimes you might cover a lot of distance in a short time, and other times a longer distance in a longer time. So it may change. So strictly speaking, we say your average speed is how far you go divided by how long a time it takes.
Yeah, so when you put a bar over a variable, that means average. You'll almost never see that in this class. What this could be useful for is like if you're on a long road trip, you cover like several hundred kilometers, it takes you like many hours, right? You can say, okay, I went like 300 kilometers and it took me 5 hours. And then you can divide it out. You know, sometimes you're going fast, sometimes you were like filling up your gas tank. But in this class, like those equations up there, those V values are instantaneous values, like how fast you're going, like at that exact moment, which is different than putting the bar over it. You hardly ever see the bar in this class.
Now we're going to talk about an idea that is considerably more involved, a little more difficult. And it's not how fast, and it's not how far. It's the rate at which you change how fast, and that's acceleration. Let me just define it. Acceleration equals a change in speed, a change in velocity, change in motion. Keyword change. Over some time interval, which I'll denote as t. If a system moves and changes how it moves, then that system is accelerating. Let me give you an example. You're standing at the racetrack, you and your friends, and you've seen cars scream by, screeching rubber, okay? 200 miles an hour here, 200 miles an hour there, 200, just 200 miles an hour screaming road. And your friend says, wow, man, you see the cars accelerate. And you say, as a matter of fact, I didn't. Your friend said, well, 200 miles an hour, man, come on. 200 there, 200 there, 200 there, 200 there. What's the change? No change. If there's no change, then there's no acceleration. Give you an example over here.
Wow. All right. So what would you feel like inside that race car? Because you're going 200 miles an hour, just constant velocity, just straight forward. What would it feel like inside that car? Would you feel just like you feel in this room, just kind of sitting at rest? Yes, you would. Yeah, it'd be just like that. You might feel like rumbling around a little bit, but you would only feel a push back into your seat if you stepped on the gas pedal and sped up, right? So you'd have to, you have to change that velocity to feel something.
Here I have a piece of metal. I'm going to hit the metal at constant speed. What's the acceleration? Begin with a Z, end with a P. Zip. No acceleration, see? It's moving without accelerating. Okay, it has speed, it has velocity. Now, when I get it started, I have to, when I get it started, it accelerates briefly, but then it just moves uniformly. So acceleration means there must be a change. And I can put this in shorthand notation, say, like that, and I can give you a numerical example. Let's suppose you're buying a car and someone says, hey, this car is really, really neat. Doesn't look very nice, kind of a little bit tacky, but this thing will accelerate. This car will go from 0 to 60. What's the person telling you? 0 to 60 miles an hour. Does that tell you anything? Then you buy the car and you find out it takes you half an hour to get up to 60 miles an hour, okay? So when you talk about acceleration, you talk about how long does it take to do that? Well, let me give you an example. If I have a car that'll go from 0 to 60 miles an hour in 10 seconds, what's the acceleration? Try it. Let me help you. The car is going to change its velocity by how much? From 0 to 60 miles an hour, okay? So there's going to be a change in velocity of 60 miles an hour, right? Did I tell you how long it would take to do that? 10 seconds. So I'll divide that by 10 seconds. S per second. So you know what the acceleration of my car is? Anyone have a calculator? Maybe you can do it in your head, okay? Okay, okay. It's going to be 6 miles per hour per second.
Ah, you guys see that? So that's the rate that speedometer needle is moving, isn't it? Every single second, it picks up another 6 miles per hour, right? So that after 10 seconds have elapsed, it's up to what number? 60 miles per hour. Hey, but you could make an equation out of that too, right? Like the velocity it picks up to is just acceleration times time, right? 6 times 10 is 60. Okay. Now, take a look at those units, miles per hour and then seconds. Now, we'll almost never talk about miles in this class or miles per hour. But you have used a different velocity unit this week, which is meters per second, right? The speed gates were reading exactly. So meters per second, right? Now, miles per hour, meters per second, that's the same idea, right? Some kind of distance per time. And if you did have meters per second for like velocity or change of velocity, could you take meters per second here and then the seconds and combine those seconds? And wouldn't it be meters per second per passing second that would change? Hey, could you combine those 2 second units and make meters per second squared? You could do that, couldn't you? Right. So whenever you see meters per second squared, you know that is an acceleration unit that has something to do with the change of velocity.
Take a piece of clay and drop it. Did it accelerate? How do you know? How do you know? Because you saw it change. You saw it up here at rest. Did you see it gain speed? Let me try it from up here. Can you guys see it gain speed when I drop it? Did you see it pick up speed? Very difficult to tell, but you know it does pick up speed. You know that intuitively, because if I took this clay and I hold it above and I say, would you dare to catch this? Dare to? You dare to catch it? Okay. Now we're gonna do the same thing. I'm gonna go on an airplane. I'm gonna drop it and you catch it. Would you dare to catch it? No way, because you know, as this thing is falling, it's gonna pick up speed. Isn't that right? And to say it picks up speed is to say it's gonna be undergoing a process, begin with A called acceleration, okay? And that pickup in speed, that's what acceleration is. And we just saw here, this thing does accelerate. Let me tell you how much it accelerates. It turns out that a freely falling object at the surface of the Earth will have a constant acceleration. And that acceleration will be 10 meters per second every 1 second. Freely falling objects will pick up a speed of 10 meters per second every second they're falling. And I can call that like this. 10 meters per second square. When acceleration is due to gravity, it's common to let the A be a G. So we could say G for the planet Earth is 10 meters per second, or 10 meters per second square. What's that mean? That means this. Let's suppose I drop this. And there's a speedometer on there. And you guys are looking at the speedometer with a spyglass. Right now, what does the speedometer say? 0. Now, when I let it go, does the speedometer reading pick up? It picks up. At the end of 1 second, the speedometer reading gets up to how much? 10. That's right, because it's been falling for a whole second. So now it's going 10 meters per second, okay? 1 more second, it's going even faster. How much 1 more second? 10. Now it's up to 20. And up to the 3rd second, it picks up another value of how much per second? 10. So how fast is it going to the end of 3 seconds? How about 4 seconds? Can you do big numbers? How about 10 seconds? How fast is it going? If that's what acceleration is, we can tell how fast things go by just saying this. The velocity that something the velocity acquired when falling is simply equal to the acceleration times the time. And if the acceleration for free fall is always 10, then the speed something picks up is simply going to be 10 multiplied by that time t. That's what we just did. I asked you people, I said, if you go for 10 seconds, fall for 10 seconds, how fast is it going? Where the t is, you put 10. And that cancels out one of these seconds over here. And so what you're left with is 10 tens is 100 meters per second. So a freely falling object will pick up to a speed of 100 meters per second if it's got 10 seconds to fall. You know what we're doing, gang? We're forgetting about air drag. We're not going to count air drag. If I take this book and this piece of paper and drop them, the book accelerates much more than the paper. Why? Because the paper, there's a lot of air resistance compared to the weight of the paper. If I take that paper and make it smaller, so now the air resistance acting on it's not going to be so much, they'll fall together. Okay. And we're only taking the case, these are relationships here. These are for the case where air resistance doesn't count.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons.
So he's going to test this on the moon. Now, the moon doesn't have an atmosphere, right? So there's definitely no air drag. It's like standing in a vacuum. Let's see. Feather versus hammer. Here we go.
For a falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? They'll hit the ground at the same time. How about that?
Oh, yeah.
The average speed when acceleration is constant is simply the speed you begin with plus the speed you end up with divided by 2. Average it.
What's that?
And then multiplied by the time of fall.
We're just going with this one. Right. So last few videos we look at what is speed or velocity. What is acceleration? What's that relationship? So now let's get into what was the last column on the table I gave you guys yesterday with dropping the ball off a cliff, which is how far has something fallen. Now, I derived an equation for you guys looking at the area under velocity versus time, because that would also represent some number of meters, which is like how far, right? Got 1/2 AT squared. He's going to derive it a little bit different method, right? But it'll tell you the relationship between how far something's fallen as a function of how much time it's been falling for. Okay?
But we're always gonna take the case where the initial speed is 0. So we're simply gonna end up with the speed we end up with at the end of any time interval, divided by 2, multiplied by the time. And what's the speed that an object will have after it's fallen? Just in general. For 1 second, we know it's 10, but how about t seconds? Anyone know? Do we have any relationship for how fast something falls? Right here. In fact, if the acceleration is g, the speed is going to be gt, the one we had right over here. So let's put that over here. See what we have here? Is this time and this time the same? This is the time that it was falling. And this is the time it was falling too. They're the same time. So I can say, I can make this a little bit more shorten up. And now I have a relationship for how far something falls.
And we did that one yesterday. All right, so last one of these.
You're on the mainland. You're up country, mine country, California. You're out with your friends. And your friends there, and someone opens up an old mine shaft. Musty. Someone says, geez, I wonder how deep that is down there. Dark. Dang. You hear the bats. Straight down. Someone says, gee, I don't know, if we had a rope, we could lower the rope and find out when it hits the bottom. So look, the ladder's all broken. There's no way to find out how far down that goes. You say, wait a minute, hand me that rock. Friend hands you the rock. You take the rock. 5 seconds it takes to hit the ground. Disregarding the time it takes for the sound to come back up. Took 5 seconds to hit the ground, right? Someone says, well, how deep is it? And you say,
So it's been falling for 5 seconds. How far is it falling? What's the answer? Okay, so it's picked up to a speed of 50 meters per second. Right, that's like velocity equals acceleration times time. Right, so yeah, 10 times 5 is 50 meters per second. But how far in meters? Right here, or maybe the answer might be in your notes from yesterday.
5 seconds. 5 5's 25. 25 times 5. It's about 125 meters deep. Some say, how'd you know that? And you say, college.
125 meters. College. So switch over here. I got just enough time to do the rest of the class here. So here we go. So you guys saw he was doing distances 1/2 AT squared. As long as you start from rest, that's if v naught 0, right? If you have 0 acceleration, just distance equals speed times time. If you have both acceleration and a non-zero starting, just add them together. Okay, so there you go. Okay, so I'm going to take that and let's just do the simplified version. So just the falling distance is 1/2 AT squared if you start from rest. Okay. So say falling distance is 1/2 AT squared. Except that I'll go ahead and do what he did and make the A and G for free fall gravity. Gravity field is a type of acceleration, so it applies here. Okay. Okay. And there's 3 ways you can go with this equation. Right? There's 3 things you could solve for. As long as you know the other 2 things, right? For example, if you know gravity, the acceleration rate and how much time it's been accelerating for, you can solve for how far it's gone. That's what you just did. If you know x and t, you could solve for g. If you know x and g, you could solve for t. You guys see that? If you know any t, you could solve for third. Let's go through each one of those, and then I will set you guys up with activity with friends. Oh yeah. So first one we'll do. Well, let's do exactly what you did. I'll just copy paste this example right here. If you're on Earth, then you know that gravity, free fall gravity is 10 meters per second squared. And so suppose something's been falling for 5 seconds. That's exactly what you just did, right? Now, don't forget to square the time. That square only applies to the t, right? This time. See how far something would fall in 5 seconds. Well, 5 squared is 25. Half of 10 is 5. Hey, if you have 5 quarters, how much money do you have? $1.25? Ah, it's a 5 times 25. About 125 meters deep. How'd you know that? College. There's that one. Oh, how about this? Let's do a new scenario. Start over. Same equation though. Let's go. Let's go to the edge of a cliff on Mars. You guys want to take a field trip to Mars? Boop, boop. Right on the magic school bus. Now we're on Mars. We found the Spartian cliff. We gotta drop this ball off the Spartian cliff. Let's say we measure the height of this cliff to be, I'll say h equals 150 meters. Right. So h is kind of like where the x goes, right? X is how far, h is the height, which is also how far. So it's going to feed into this equation, 1/2 gt squared. Okay. Except this g is no longer 10 meters per second squared because we're on Mars. Hey, I wonder how long it would take this ball to reach the ground. Okay. Well, you got this astronaut buddy here. He's going to time. Here's a stopwatch, and he gets a time of 9 seconds. It takes 9 seconds for this ball to fall 150 meters on Mars. Who can tell me what is Martian gravity equal to? It takes 9 seconds to fall 150 meters. You guys did that? Right, who figured it out? Yeah, what you got? 16.6. Ooh, okay. I got some a little less than that. Aha! Caitlin got it. 3.7 meters per second squared, right? 3.7 meters per second squared. All right. So here, I gave you guys this height change in this time. So those numbers feed in right here and here. Okay. We're solving for g. Now it's just a couple of algebra steps. Okay, cross multiply the 2 and divide down the 9 squared. So what's 150 meters? Multiply this 2 over. So it's times 2. Divide down 9 squared. It's like 81 in square seconds. Right. That's equal to the free fall gravity on Mars. Okay. Ooh, do you guys see this unit right here? Meters per second squared. Excuse me. Sorry. So that's going to be that's going to describe an acceleration. Now we just need the numbers. What's 2 times 150 over 81? 3.7 meters per second squared is Martian gravity. All right. All right, guys, right there. All right, but there's one more thing we could do with this equation, which is solve for t given h and g. Right? Richard? Okay. So let's do that. Say the height that something falls, height drop is 1/2 gravity field t squared. Okay. Huh. How about t? You know what? Let's solve this in terms of variables. You guys think you can do that? Cross multiply the 2 times the height drop is equal to gt squared. Divide the g down. So 2h on g is equal to t squared. And what's the last algebra step to extract t? What do you have to do to both sides? Take the square root. Square root. So the time of fall would be the square root of, and we get this expression. G. Okay, so if you knew how far something fell, that's what h is, like a height change. And you knew the free fall gravity of the planet, which on Earth is 10 meters per second squared, you could calculate how long it's been falling for. It box this in, because you guys are about to apply this to yourselves. I'm not dropping any of you guys, but you're going to be dropping a ruler. Do you think, guys, that you could pair up with a partner and then do the setup, and then one person holds the ruler, one person has their fingers at the 0 centimeters and catches it as soon as they can? Okay, let me draw that out. So you guys got some rulers on your desk. Okay. One person is going to like hold the roller up here. Okay. And then another person, have your fingers at the 0 centimeter mark. It's like finger and thumb, and then okay. And then the person holding the roller up here, you drop it, and the person down here at here's 0 centimeters. This is the 0 centimeter mark. Okay, you're going to catch it as fast as you can, and then won't the roller be not only falling but falling faster and faster because it's going to be accelerating. It's going to be picking up 10 meters per second squared. It's going to be falling faster. So whatever mark you catch it at, can't you use that to back calculate what your reaction time is? Right? Hey, what do you guys think the average human reaction time is? There's a delay between what's going on out in the world and what's going on inside your head. It's a fraction of a second. You guys are about to figure out what that time is. Let's run an example. Make sure you guys can do this. Suppose I drop the roller and my friend catches it at 19 centimeters, 19 centimeter mark. Okay. If the roller's been falling for 19 centimeters, what is your reaction time? You know what? You guys try it out. Apply that formula for 19 centimeter drop, and then tell me what you get. 19 centimeters. It's been falling. Okay, so if you catch it at 19 centimeters, who knows what your reaction time is? What'd you get? Ooh, okay. Now, whatever number you get, now think about that for a moment. Does it make sense? What'd you get?
1.95.
Okay, so I'm hearing 3 point something. I'm hearing like almost 2, that almost rounds to 2. Guys, 3 seconds, 2 seconds. If you catch a roller after 19 seconds, does that sound like it's been falling for about 2 or 3 seconds? No, that didn't really make sense, right? Right. I kind of gave you guys sort of a trick question. Not really, but kind of. Because if you plug in 19 here for H, that'd be 19 centimeters, right? But this gravity is in meters per second squared. Don't you have to reconcile the units first? So you don't want to plug in 19 for H. Because if you plug in 19, what you're saying is that 19 of these meter sticks just fell through your hair. You're like, whoa, like 19 of those. And that would take about 2 seconds. Okay. No, that's not what we're saying. Guys, 19 centimeters. What number do you actually plug in for H? How many cents in a dollar? 100? How many years in a century? 100? So how do you convert from centimeters to meters? Divide by 100. So let's go 0.19 meters. Still 10 meters per second squared. See what this person's reaction time would be. What's the square root of 2 times 0.19? Okay, 0.19 something seconds. Does that sound reasonable? Reaction time? Yeah, that sounds about right? Isn't that about 1/5 of a second? About 1/5 of a second? And that right there is the average human reaction time. So if you catch the roller faster than that, then good for you. All right, so we got just enough time. We got 2 minutes left in class. Go ahead and pair up, do this with each other for fun. I'm not going to pick this up as an assignment, but yeah, that'll carry us all the way to the weekend. That is a wrap on today.